state of a particle can be 0 or 1. And also you can think that it can be, a superposition of 0 and 1. So in other words, it can be, probabilistically distributed between 0 and 1. So there you go. There is something called probability, and you have to really determine the state probabilistically. And so this principle is called principle of superposition. Another principle is entanglement, where states are coupled together. And this is very important as far as quantum communication and quantum computation is concerned. So in entanglement, what happens is a state of a particle is coupled with another state. You cannot really decouple the states. They go together, they're coupled. It doesn't matter how far the particles are, apart. So their states are coupled together. And this concept is called entanglement. So superposition and entanglement are two of the most important phenomena that are essential to design a quantum computer or quantum system. Now, so I've talked about certain, some phenomena, right? Quantum phenomena. And I said that fundamentally these arise from the fact that there is non-locality, Quantum computers are based on primarily superposition and entanglement. Whereas there can be a bunch of devices that will be based on other phenomena. For example, think of laser, or LED, These devices are based on quantization. As I said that electrons' energy are quantized, certain discretized forms are allowed. So when an electron makes a transition between a higher level, energy level, to a lower level, in other words, when an electron loses energy, it actually emits light. And the color of the light will depend on how much energy is lost in that or during that transition. So if you can define states, certain well-defined states, and if you let the electrons, go from the higher to the lower state, it will emit, monochromatic light. It means a single color light, So the purity of the light will depend on the discreteness of the system. If you have really good, highly discretized energy levels, then the light emitter will really be, good, in terms of frequency and the color emission. So tunneling, for example, right? So you can think of devices based on tunneling and phenomenon, right? So in other words, quantum computers, you can think that quantum computers are basically a subset of the quantum devices. So quantum devices, even sensors, can be designed based on quantum features. But sensors not necessarily are quantum computers.
Right.
So quantum computers primarily depend on the principle of superposition and entanglement. And there are many other devices that can depend on other quantum phenomena.
Well, you mentioned that when we were talking about the LEDs and laser systems and stuff are based on the principles of quantum mechanics, and some of your research is in nanoscale devices, which are also reliant on these quantum mechanisms. And I was wondering, specifically one of the projects that you oversee is one of the electronic scale of quantum dots. And I was wondering, we talked a little bit about qubits and how these principles of superposition and entanglement are important in how these mechanisms are used to actually create devices. And I was wondering if you could explain a little bit what is a qubit, what is a quantum dot, and how are these important in the development of nanoscale devices?
Excellent question. So as I said, engineers must design devices based on certain principles or phenomena, right? So quantum dot, you can think it's a playground, where you will see quantum features coming up, So quantum dot is an artificial atom. That is how the community actually, recognize a quantum dot. So think of an atom. So in an atom, you have essentially, a quantum cavity, like a quantum well, a potential well. An atom is nothing but a trap for an electron. It traps electrons, but the trap is very small, less than 1 nanometer. When an electron is confined in an atom, it is confined because there is a nucleus. And nucleus actually is the source of potential. So nucleus is essentially giving you that potential cavity, and the electron is trapped in that cavity. And so you can see that electron's energy is quantized in an atom. You have all these orbitals. Chemists call these orbitals, right? 1s, 2s, 2p, all these orbitals. And these orbitals come in discrete forms. Now, quantum dot is a man-made atom. You can think this way. But the quantum dot is bigger than an atom, obviously. It can be between 2 to 10 nanometer, for example. But still, it provides strong confinement for an electron. As I was saying, that when an electron is trapped in a small domain, in this case quantum dot is that domain, the electron will exhibit certain quantum features, like quantum quantization. So therefore, quantum dots can be used in lasers, in LEDs, and you can see modern TVs, right? You see quantum dot LEDs, right? Isn't it? So quantum dots are nothing but devices that allow you to really, generate quantum features. Now, the most important quantum feature that is available is from quantum dot is quantization. Quantization. So quantum dots can be used, for example, you are talking about applications, isn't it? Where they can be used?
Yes.
Quantum dots. So quantum dots can be used in many different applications. For example, as I said, LED or laser, where you need, pure light emission, pure in terms of color or frequency. Quantum dots can also be used as sensors, even in biosensors, you can use quantum dots. Because, whenever, let's say think in simple terms, let's say a cancerous cell, a cell can be modeled in terms of potential. So a cancerous cell will have different potential landscape compared to a good cell. A bad cell will have a different potential landscape compared to a good cell. So when you attach a bad cell to a quantum dot, what happens is the potential changes, overall potential changes. And potential is very important because electrons interact with the potential. And electrons' energy depends on the potential. The Schrodinger equation tells us that in the Schrodinger equation that defines quantum mechanics, that describes quantum mechanics, you have a potential term in that equation, and if potential changes, electrons' energy changes. So therefore, if you bring a cancer cell to quantum dot, the potential landscape changes, and so energy also changes, and so let's say optical emission also will change. So by looking at the optical emission, you detect that, oh, this cell is bad compared to the good cell.
Okay.